Hello and welcome to my channel. In this video we will learn about axiomatic approach to probability. Okay, so we have studied the probability in the earlier classes. Okay, and there we have studied the probability definition in terms of number of favorable outcomes to event, the event which is we are finding the probability, divided by the total possible outcomes, right? So there were formula there. Now there is another way of learning, or there is another way of knowing what is probability, and that is nothing but axiomatic approach. So axiom means actually, so we have something called as axiom. So axiom is a thing which is not proved, but it is taken to be true. Okay, the axiom is what? It is a thing, it is a statement which is not proved, but it is taken to be true. So let us look at the axiomatic approach to probability. Okay, so let us consider a sample space of a random experiment. So let S be a sample space of random experiment. Okay, then the probability is nothing but a function, is a real valued function. Okay, is a real valued function whose domain is the power set of sample space S. Okay, so probability is the real valued function whose domain is the power set of S, and range is the interval, 0 to 1, closed interval 0 to 1. Okay, satisfying the following condition, satisfying the following condition. So let us look at the conditions. Okay, but first of all, what is probability? Probability is just the real valued function whose domain, okay, domain means what? The set from which the function is assigned. Okay, so domain is the power set of S. You know what is a power set, right? So power set is nothing but set of all subsets of the main set, that is S here. Okay, and range is what? Range is the value that the function takes. So the range is in the interval closed 0, 1, satisfying the following condition. So let us look at the conditions. So first is for any event E, probability of E is greater than or equal to 0. Okay, second, probability of this whole set, the sample space, is 1. Okay, and third, if E and F are mutually exclusive events, if E and F are mutually exclusive events, right, then probability of E union F is equal to probability of E plus probability of F. Okay, so this is the formula. So these are the three conditions that the probability function satisfies. Okay, now let us find the probability of empty set. We have to know what is the probability of empty set. So now let E be any event, okay, of course of the sample space S, and F be empty set. Okay, then if we find out this probability of E union F, and that is nothing but probability of E union empty set. So what it will be? It will be nothing but probability of E plus probability of empty set. Why? Because E and empty set are mutually exclusive. E and F, that is nothing but empty set, are mutually exclusive. Okay. So why they are mutually exclusive? Because you know that E intersection F, that is nothing but E intersection empty set. Okay, E intersection empty set is nothing but empty set, right? So this we have. So this implies probability of E union F is what? Empty set, right? Is equal to this probability of E plus probability of empty set, right? So this implies probability of, now E union empty set is what? Any set union empty set is the set itself, that is E. This is equal to probability of E plus probability of empty set, right? So now what happens is this gets cancelled, probability of E, and what we have is 0 is equal to probability of empty set. So what is the probability of empty set? It is 0. Okay, so this we have found out by the axiomatic definition of probability. Okay, now let us derive 3 more conditions from the same axiomatic definition of probability. So let us take, let S be a sample space with outcomes. So first outcome is denoted as omega 1, right? Second outcome is denoted as omega 2, and so on up to omega n. So that is S is nothing but the set of omega 1, omega 2 up to omega n. Okay, so all these sets are simple sets. Okay, that is these events, if you take omega 1, that is a singleton set here. Okay, so instead of writing this here omega 1 like this, we simply write it as omega 1. Okay, this actually is a set, this is also a set. So instead of writing this brackets here, we directly write. Okay, so what we have is sample space is equal to the set of all these outcomes, right? Then by the axiomatic definition of probability, then by the axiomatic definition of probability, we have, so first thing what we have is this, 0 is less than or equal to probability of each omega I less than or equal to 1. Okay, so this we have. So what is the statement here? It is the probability of any outcome omega I is always between 0 to 1. So this is for all omega I belonging to the sample space. Okay, that is the first thing. Then second is this, probability of S is 1, right? So right now we are writing only the statement which is there in the axiomatic definition here. This is the second thing we had, so that only we will take, but we will derive another statement from this statement. So probability of S, so this implies probability of omega 1 union omega 2, right, union omega n is equal to 1. Now since these are sets, okay, these are mutually exclusive sets, right? So omega 1 union omega 2 up to union omega n will be nothing but S, right? So this implies probability of omega 1 plus omega 2. Why I am getting this? Because all these sets are mutually exclusive. Okay, mutually exclusive. So probability omega 1 plus probability omega 2 up to probability omega n is equal to 1, right? So this is what we have. Okay, this is the second statement. Now third statement, let us see. So now let us take this. Okay, any event, for any event E, for any event E, right, a probability of E is nothing but summation, summation only will write summation probability omega I. Okay, where this omega I all belong to the event E, right? So probability of event E can be given as summation of probability of each outcome omega I in the event E, right? So this is the third statement. Okay, so now this was only the conditions that we derive from the axiomatic definitions of the probability. Okay, so now let us look at something called as the probabilities for equally likely outcomes. Okay, so probability for equally likely outcomes. So this is the next subtopic. Okay, now let us take sample space. Let S be a sample space of a random experiment, okay, given by this, given by S equal to set omega 1, omega 2 up to omega n. Okay, this is the sample space of a random experiment. So now let us say that the outcomes are equally likely. Let the outcomes of the random experiment be equally likely. Okay, that is what, that is the chance of occurrence of each simple event, right? Chance of occurrence of each simple event, that is omega 1, omega 2, omega n, is the same. That is the chance. Okay, let us write it properly. The chance of occurrence of each simple event okay, each simple event is the same, right? So if you look at the example, one example, if you, that is tossing a coin. Okay, so what is the sample space? It is head and tail, right? So what is the probability of occurrence of head? It is half, right? 1 by 2. Also this, the probability of occurrence of t is half. So you can see that the outcomes in this experiment H and T are equally likely because their probability is the same. So in same way you can generalize this. Okay, so that is the probability of omega I is equal to P for all omega I belonging to S, right? And where this P is between 0 to 1, right? So that is the thing. Now let us see. So what you have is this, right? And now if we take this, so now we know that probability of a sample space is 1, right? So this implies probability of omega 1 plus probability of omega 2 plus probability of omega n is equal to 1, right? So this implies p, right? Probability of all the outcomes is same, p. So p plus p up to p is equal to 1, right? So how many times this is? So 1, 2 up to n, right? So n times. So this goes up to n times. So what we have is this implies np, right? When we add the same quantity n times, what we get is n into the same quantity. Okay, so that is equal to 1. So this implies probability is equal to nothing but 1 by n. This is the probability p. So if you have equally likely outcomes and if there are n outcomes, then probability of occurrence of each outcome is given by 1 by n. Okay, so that is the derivation that we did. Okay, now let us take one statement here. So let S be a sample space of a random experiment and E be the event of the sample space. Okay, such that what happens is number of elements in the sample space is n and number of elements in the event is m. Okay, now if the outcomes are equally likely, right? If the outcomes are equally likely, right, then what we will have here? Then we will have probability of E will be nothing but this. So there are m number of outcomes in E, right? So what we will have is this 1 by n, because you know that the probability, if the outcomes are equally likely and if the number of elements in sample space is n, then the probability of each outcome in the event, or in general probability of each outcome in the sample space is 1 by n. So 1 by n plus 1 by n up to 1 by n. Okay, now we have to look at how many times this occurs. Now the probability of outcome of first outcome in the event E is 1 by n, right? And the probability of second outcome in event E is again 1 by n. Then up to the probability of the mth outcome in the event is again 1 by n. So this here, how many times it occurs? M times, because there are m outcomes in the probability E, right? So what will happen is, if you add one same quantity m times, you will get m times the same quantity, right? So this is equal to m by n. So that means probability of E is equal to m by n, right? And so this is one formula you have here, and which we have studied in. Okay, now let us see. Right now from this formula what we get, probability of E is number of favorable outcomes, to E, okay, divided by this n is nothing but total possible outcomes, and this formula we have studied in the earlier class, 10th class. Okay, so what we have done here is we have derived the formula using the axiomatic definition of probability. Okay, we have derived the formula using axiomatic definition of probability. So that's it in this video. If you have liked my video, please hit the like button. If you have not subscribed my channel, please do subscribe. I will see you in the next video.